Last time I introduced the concept of fugacity from a mathematical standpoint. I derived the following equations. So remember that in these equations, the Greek letter phi is the fugacity coefficient, and it is the fugacity divided by the pressure. Remember, the units of fugacity are pressure, so the phi is a dimensionless constant. We derived these equations. I derived the first one and then told you what the second one was by analogy. So this is kind of like the departure functions where you use whichever one is more convenient. That discussion from last time I realized was very theoretical, very mathematical. Today I'm going to try and dial it back a little bit and explain to you why you would need to know fugacity and how you would use it in your everyday life as an engineer. I want to do that in the context of one of my favorite household appliances, which is the air conditioner. I just got my air conditioner replaced in January, and in the process of doing that, I took it upon myself to learn exactly how it works such that I can make an informed decision. And I was actually surprised by myself and how little I actually knew about how the air conditioner works. So let's say this is my house, and I like to keep my inside temperature nice and comfortable at 75 degrees Fahrenheit. I just checked the weather today in Gainesville outside. It is a toasty 86 Fahrenheit in the middle of the day. And outside is a large environment. I'm going to assume that this is a heat reservoir. In other words, this 86 degrees is going to be constant until the sun decides to go down or until it decides to rain and drop the temperature. The temperature of the outside is completely unaffected by whichever temperature my house is. But because my house is a smaller system, its temperature is susceptible to changes. And because we have thermal contact, so I have a bunch of windows in my house, and the entire house is walls, which is in thermal contact with the outside, obviously, the laws of thermodynamics are going to want to heat the inside of my house. So heat is going to want to flow from the outside into my house, which is going to raise the temperature of my house into the 80s, which is less comfortable, obviously, than 75 or below Fahrenheit. So what the air conditioner does is it is able to transfer heat from inside of your house to outside of your house at a rate that is greater than the heat transfer from outside to inside. So the net effect actually is that there is no heat transfer inside. The net effect is that there's just heat transfer outside. And at first glance, this appears to counteract the laws of thermodynamics. How can I have heat that is being transferred from a colder body to a warmer body? In order to answer that question, we need to go into a little bit more detail on how an air conditioner actually works. So I remember when I was 12 years old growing up in Michigan, my family got our first central air conditioner. And wasn't that we were going without an air conditioner. It's just not that necessary in Michigan because it's not as warm of a place. But I remember I saw this box installed outside, and I thought that that was just the entire air conditioner. Turns out that this is only a portion of it. So the portion that most people think of when they see an air conditioner, this is called the condenser. And if you ever peeked inside one of these things, you've seen it's got coils on each side that kind of serpentine through like this. And that's because this is a heat exchanger. And what is going in through all these coils is the refrigerant. And at the inlet of the condenser, the refrigerant is in its vapor phase, and it is high temperature and high pressure. And as it goes through the condenser, as the name implies, by the time it exits the condenser, it has been condensed into a liquid. But it is still at high T and high P. Right, because the phase change that occurs, I've introduced this in a couple of other videos. Upon phase change, I have phase equilibrium. I don't change temperature and pressure. So temperature and pressure remain the same. The only thing that's happening is, like I said, the phase change. So what provides the heat duty required to condense this vapor into a liquid? I need to remove heat somehow. So the enthalpy of the vapor is higher than the enthalpy of a liquid. So I'm going to go ahead and say this is molar enthalpy at state 1, and this is molar enthalpy at state 2. And because H1 is in the vapor state, it must be greater than the molar enthalpy in the liquid state. So what provides the driving force for heat transfer? Oops. Well, on the top of the condenser, there is this fan up top. And the fan blows air out the top, which creates negative pressure inside. So that means it's drawing air from the environment from all sides of the condenser. And that convection is what actually drives the heat transfer. So there has to be a temperature difference between the coils and the outside. So that means that whatever temperature this H1 is, it must be greater than 86. So this high temperature is greater than 86 Fahrenheit. All right, and that is because I need to transfer heat from the condenser to the environment. Now the environment, of course, doesn't change temperature. Like I said, it's large enough that you assume it can stay 86 degrees Fahrenheit. But the point is that I'm dumping heat out into the environment. Okay, so let's follow the state of my refrigerant. So it comes out of the condenser. It is liquid at high temperature and high pressure. It's going to go into the house now, and as soon as it gets into the house, it is going to undergo expansion. So this expansion valve is going to reduce the pressure and thereby reduce the temperature. So it's still a liquid at this point, and liquid at low T, low P. So anytime I reduce the pressure of something, it gets colder. So imagine if you've ever dusted your keyboard with one of those cans of air. It's not air, but you get it at Office Depot and stuff. If you ever sprayed your keyboard with one of those, you might have noticed that the can gets very, very cold. And that's because of the expansion that's going on. There's high pressure gas in there, and you are throttling that gas and making it a lower pressure. So I am making it such that the temperature of my refrigerant is now dipping below the 75 degrees Fahrenheit. And that is absolutely critical, because the next step of what happens, this refrigerant is going to go into my air handler. This is not right in the middle of your house as I'm drawing. This is my particular air handler is in the garage, but it takes, the ductwork takes the air from inside the house and contacts it. And the evaporator is what it's called. Evaporator is inside the air handler. And it also is a heat exchanger, so it's got this serpentine coil pattern as well. In the evaporator, what happens is liquid is transferring phases from the liquid phase to the vapor phase. Very similar, but opposite to the condenser. So I've got a vapor at low T and low P. However, so how does this happen? I need to gain energy. So I need to have an energy input into the refrigerant in order to vaporize it. And that comes from the ambient energy of the house. So say that my thermostat is set at 75 degrees Fahrenheit and the actual temperature is 76 degrees Fahrenheit. I'm going to have heat coming from my house that is going to transfer to the evaporator coils, which is going to provide the energy needed for this liquid refrigerant to boil or to evaporate. Same thing. All right, so now I've got this vapor refrigerant that is at a low temperature and a high pressure. How do I complete this cycle? The last step of the air conditioning cycle is I have to send this vapor now to a compressor. And this also happens right inside the house. The compressor takes the vapor and keeps it at, it increases the pressure, which also increases the temperature. Vapor, high T, vapor at high T and high P. In order for this to work, I need to input some shaft work into it. So this is where the energy requirement comes in. When I get my energy bill every month and it says I use so many kilowatt hours, a large portion of that is due to the shaft work that I need to power my compressor in order to compress this vapor at a low temperature, high pressure state to a high temperature, high pressure state, such that it can go to the condenser and this whole loop can continue. All right, so how does this relate to fugacity and to phase equilibrium? Well, there's two steps within the process at which I have phase equilibrium. I've got a condenser. Definitely I have a phase change going on in the condenser, and I have a phase change going on in the evaporator. And in the old days, most of the refrigerant that was in these refrigeration cycles was Freon. And Freon was problematic because it is very harmful to the environment. So air conditioner companies were faced with a conundrum. They had to find a replacement that worked just as well. So Freon works because of its thermodynamic properties. You could easily specify, if you studied it well enough, you could specify the exact temperatures and pressures that you would need to specify all over your system in order to get this behavior to occur. So what has to happen is that the enthalpy of the vapor has to be greater than that of the outside air. So the high temperature makes it so that heat is transferring from the refrigerant to the outside. That requires that the temperature is hotter in the vapor phase than the outside. And it also has to be in its liquid state at low temperature, low pressure, its enthalpy has to be low enough. So this would be H3 and H4 would be up here. The enthalpy has to be low enough such that it sucks up heat from the inside. So it has to have enthalpy that is a function of temperature and pressure that is known. Going back to the Freon part, if I have to get rid of Freon, I need to find an attractive alternative. How do I do that? One option is I could take a candidate chemical, a new one, maybe that's a little bit better for the environment, and I could do a lot of experiments on it. And I could develop the complicated enthalpy temperature diagrams needed in order to specify this system. Or what I could do is just collect enough data such that I could accurately model it with an equation of state. I would need to know a couple of other properties, but without doing an exhaustive list of experimentation, I could use the fact that fugacity of the vapor must be equal to the fugacity of the liquid at phase equilibrium. That seems like a very large jump to make, but in the next video, I will show you exactly how you could do this calculation in order to determine what the vapor pressure is of a chemical, knowing only its equation of state and its temperature.